In 6.3, we did several things in analyzing polynomial functions. One thing was to look at a polynomial and be able to say whether it was a polynomial in 1 degree. So if you see these 3 examples, A is a polynomial in 1 variable, not a degree. It has just x throughout. That is the only variable in A. Its leading coefficient is 8 because the term with the highest degree is the 8x to the 5th power. So its degree is 5 and the leading coefficient is 8. B, you can see, is not a polynomial in 1 variable. It has the y. So you see xy here in this term. It's not a polynomial in 1 variable. Down here in these 3 examples, we go back to those definitions of what makes a polynomial. And so 1a here is not even a polynomial because you have this term where you have a fraction over a variable over x. So we don't even consider it. It's not even a polynomial. So we need to remember those definitions. We discussed briefly the remainder theorem so that we could evaluate functions. This goes back 5 and 6 to chapter 1, where we could evaluate w of x at 5 by replacing the x's with 5 and then do 5 to the 3rd power times -2 plus 3 times 5 minus 12. Or we could do our synthetic division. So this is where I'm evaluating w of -4. So if I take my coefficients, and of course we're missing the x to the 2nd term, so I do have this 0. So if I place my coefficients into my synthetic division setup, and I want to evaluate at -4, so this takes the spot of where I would place my solution, and I go through the motions of doing my synthetic division, so dropping down the -2, multiplying 4 and -2, I get 8, adding, I get 8, 4 times -8, I get -32, and adding, getting -29, multiplying those two, -29, -4, getting 116, and adding these two, I get 104. Therefore, when I evaluate wx at -4, w of -4 is 104, and so I can use what is called the remainder theorem to evaluate functions at specific values. So I could do this also for 5. So the 5 would go here, and I could go through my synthetic division and evaluate that function. When we do at variable values, then of course you would have to replace the x's with what you were given. So y to the 3rd would go here in the x, and we went through this in our notes and asked questions how we did that. Again, we went through and we found and grouped these together. We did groups of the odd valued functions, and noticed that the ends pointed in opposite directions for the degrees of 1, 3, 5. We looked at 7 and conjecture for 9. Degrees of 2, 4, and we did 6, and we kind of did 8. And noticed that the ends pointed in the same direction. And we also talked about turns. So here's 1, 2, 3 terms on this graph, which could predict that it is a degree 3, or that it has 1, 2 hills, even though this is down, hills. So it's 1 less hill than the degree it has. So if this has 2 hills, it's a degree 3. So 1 more than the hills gives you the degree. Or if you didn't, so you decide whether you're a turn or a hill person. So I see 1, 2, 3, 4 turns, or I see 1, 2, 3 hills, so I get a degree 4. Then we discussed our leading coefficients and our degrees. So when we have an odd degree, a degree of 3, a degree of 5, a degree of 7, then we have odd power functions, which means that the ends of our graphs go in opposite directions. So, and then you have to decide, do I begin down and then up, or do I begin up and then down? And that depends on the leading coefficient. Positive, we begin down up. If it's negative, it's up, down. And so that would be, we went through some examples of the polynomials. We also have even power functions, so a power of 2, 4, 6, kind of like your quadratic functions, your parabolas. So those even ones, if you have a coefficient which is positive, then it's facing up, both ends face up, or both ends are facing down if your coefficient is negative. Now remember, degrees depend on how the ends go, and then the coefficient, a larger number, the whole number in front of that degree term, depends on whether it's facing up or facing down. And then we discussed end behavior. So we're looking at these ends, and then we describe how that graph goes. And we took some quick notes about how to write this a little bit better. This f of x is approaching positive infinity. Remember, this means my graph is increasing. And this f of x is approaching down here negative infinity. That means my graph is decreasing. And then x is approaching negative infinity and x is approaching positive infinity. That just means on the left, on the right. So x is approaching negative infinity is on the left. X is approaching positive infinity is on the right. So this end behavior right here says my graph is increasing on the left and my graph is increasing on the right. And here this says my graph is decreasing on the left. See, pulling down. And my graph is increasing on the right. And yep, on the right side. So we did a few notes on that to kind of decipher what it means. And then we had zeros. We look at how many times, the most number of times possibly, that it could cross the x-axis. And we talked about real number zeros. And we just counted how many times it crossed the x-axis. Very simple. And this rule just tells you your odd degree functions over here will have an odd number of real zeros. So look, it's degree 3. It has a maximum possible of having 1, 2, 3, or 1. As in that example that it shows you. Even degree polynomials are going to have an even number of polynomials. So this fourth degree function, its most that it could cross would be 1, 2, 3, 4. It may not cross at all. It can have 0, or it would cross 2. It's not going to have 3. It's not going to have 1. It's always going to be an even number of real zeros, or none at all. And then those just puts in words that I was pointing out, whether you look at hills or you look at turns on your graph, and you can predict what your degree is possible to be.